My name is Emma Doring, and this is my Physics 2 Lab 4 Magnetic Braking with Faraday. The purpose of this lab was to observe the results of a bar magnet being dropped through a roll of aluminum foil in terms of Faraday's law, treating the bar magnet as the source of external magnetic field and the aluminum foil as the location of induced current. The fundamental principles used were Faraday's and Lenz's law, the Biot-Savart law, Newton's second and third laws, Ohm's law, and magnetic force. Faraday's law and Lenz's law were used to calculate the change in magnetic flux as the magnet fell through the tube. The Biot-Savart law was used to calculate the magnetic field of the magnet. The magnetic force formula was used to calculate the magnetic force exerted on the tube. Ohm's law was used to calculate the induced current in the tube. Newton's second law was used to calculate the gravitational force on the magnet, and Newton's third law was used to update the position and velocity of the magnet as it fell through the tube. The average time that it took for the magnet to fall through the tube in my experimental model was 1.204 seconds, whereas the time it took for the magnet to fall the same distance just through free space was 0.29 seconds. So you can see that it fell much more slowly through the aluminum foil tube, and then the time that the magnet took to fall through the tube in the computational model was 1.335 seconds. The system in this experiment was the bar magnet and roll of aluminum foil, and the surroundings was Earth. The steps that I took were identifying and labeling the north end of the bar magnet using a magnetometer app, setting up a camera and recording 5 instances of dropping a bar magnet through a roll of aluminum foil, writing down timestamps for when the magnet entered and left the tube, and calculating the amount of time that it took to pass through, then calculating the average of these times for the 5 instances, completing a code in GlowScript to model this computationally, and then comparing the models. The assumptions I made were that the bar magnet is a magnetic dipole. The only forces acting on the bar magnet are gravitational force and magnetic force, and then air resistance is negligible. So the results of my experimental model, as I said before, the time it took for the magnet to fall through the tube was 1.204 seconds, and the answers for the questions in the lab sheet are that we can't use a Ferris tube for this experiment because of its strong magnetic properties. They would create magnetic forces that would be outside of the induced eddy current. And then when I drop the bar magnet through the tube of foil, it falls 0.914 seconds slower than it does when I drop it the same distance through free space. Here are my coding details. So on the left are my initial conditions, the geometry of the aluminum foil tube, the mass of the magnet, and then the magnetic dipole moment, and then obviously the initial velocity and initial time. The first thing I did was calculate the magnetic field and magnetic flux of the bar magnet. Then I calculated the forces on the magnet. I calculated the induced current in one ring, and then calculated the magnetic field per ring and magnetic force on each ring. I calculated the net force on the magnet and then updated the position and velocity of the magnet. The results for the computational model are on the left, so you can see, as I stated earlier, the time that the magnet was in the tube was 1.335 seconds, and then you can see the image of the magnet falling through the tube and the velocity versus time graph. So in the tube, red corresponds to clockwise and blue corresponds to counterclockwise when viewed from above, because the blue current is above the red current as the magnet falls through the tube. And then when you flip the magnet around, the results would ultimately be the same, but the direction of the currents would just be flipped. And lastly, the shape of the velocity versus time plot tells me that the forces acting on the bar magnet are not equal when it's first dropped into the tube, as you can see by the way the velocity decreases and then increases, and then they are equal for some time while it's in the tube because the velocity is constant, and then they become unequal again when it begins leaving the tube. Again, there's not much difference in the computational model versus experimental model. The difference in time that the magnet takes to pass through the tube is only 0.121 seconds. To make this computational model more accurate, we could split the tube into more rings. Sources of error are human error in identifying the timestamps, the potential outside forces that could be acting on the magnet outside of the magnetic and gravitational force, and then incorrect measurement of the tube geometry. Discussion questions: if the resistivity of the conductor was reduced to almost zero, the magnet would slow down as it falls through the tube, and then if holes or slots were cut into the tube, then the magnet would fall through the tube more quickly.